Good afternoon, distinguished committee members, colleagues, and guests. I'm Saliha Mezouj from the University of Algiers. Today, I will present our research titled Advanced Ensemble Learning Framework for Reliable Smart Grid Stability Detection. This work proposes an ensemble-based machine learning framework to improve prediction, robustness, and accuracy in smart grid stability detection. Let me start with the structure of this presentation. We'll begin with an overview and the motivation behind this study, followed by the methodology used, the experimental results, and comparison with current state-of-the-art models. The presentation will conclude with our findings, the limitations we observed, and directions for future work. The smart grid represents a paradigm shift from traditional electricity networks. With increasing decentralization, renewables, and automation, ensuring operational stability becomes more complex. Traditional analytical approach often fall short in capturing this dynamic, high-dimensional behavior. This work leverages machine learning, specifically ensemble techniques, to address this gap. Here we see the key components of smart grid: generation units, transmission networks, substations, distribution networks, and consumer interfaces. These components interact through intelligent communication layers, enabling real-time data exchange and control. The complexity of this architecture justifies the need of advanced AI tools for operational stability. The rapid expansion of smart grid, characterized by decentralized sources and variable demand, requires more intelligent approaches for stability classification. Traditional models don't scale effectively under such conditions. Ensemble learning is motivated here due to its capacity to merge multiple learners, compensating for individual weakness and improving overall predictive power. Our research is guided by three core questions. 1. Can ensemble learning significantly enhance smart grid stability detection? 2. Which ensemble configuration yields optimal performance? 3. Does our framework generalize effectively across varied and unseen grid scenarios? We propose an ensemble-based framework incorporating bagging, AdaBoost, stacking, and soft voting. The models were trained and validated on a balanced smart grid stability augmented dataset using 5-fold cross-validation to ensure robustness. Our pipeline includes 4 main stages. 1. Data preprocessing, including normalization and encoding. 2. Implementation of the 4 ensemble models. 3. Rigorous 5-fold cross-validation. 4. Performance comparison using multiple metrics. This diagram architecture illustrates the flow from raw data acquisition through preprocessing, ensemble model training, and final stability prediction. Each ensemble block integrates different base learners, allowing the system to adapt and generalize efficiently. Ensemble learning combines multiple classifiers to improve prediction performance. Bagging reduces variance via resampling. AdaBoost focuses on difficult cases through adaptive reweighting. Stacking learns from combined prediction using meta-learning. Voting aggregates outputs by majority or probability averaging. Bargain utilizes 15 decision trees. Each tree is independently trained on a bootstrapped sample of the data set, created by random sampling with replacement, enabling the model to capture diverse patterns with the data. After training, predictions for unseen data are obtained by aggregating the outputs of all 50 models. The final prediction is the average of all individual predictions. AdaBoost focuses on refining weak learners by adjusting sample weights iteratively. Begins by initializing equal weights for all training samples in each boosting round. A weak learner, in our case, is decision tree classifier, is trained on the weighted data set. The classifier's weighted error is calculated and its performance is quantified using weighted alpha t, which determines the importance of the weak learner in the final ensemble. Misclassified samples are assigned higher weights. The process is repeated for t boosting rounds, where t equal to 50 in this implementation. The final prediction is made by combining the outputs of all weak classifiers weighted by their respective importance values. In the stacking ensemble framework, multiple base learners are initially trained independently to capture diverse decision boundaries from the dataset. In our implementation, the random forest and support vector machine classifier SVC are selected as the base models due to their complementary characteristics. These models generate prediction outputs that are then utilized as input features for a higher level meta-learner, specifically a logistic regression model. The meta model is responsible for learning the optimal combination of base model outputs, thereby mitigating individual weaknesses and improving overall predictive performance. The training process involves generating out-of-fold predictions from the base models which are used to construct a new dataset for training the meta-learner. During the inference phase, predictions from the trained base models are collected and aggregated to form an input vector for the meta model, which then outputs the final prediction. In our work, the soft voting model is adopted, where the final prediction is determined by averaging the class probabilities predicted by each base model. The ensemble in this study comprises three classifiers: a random forest, super vector classifier, and logistic regression. Each base model independently estimates the probability distribution over the class labels. These probabilities are then averaged and the class with the highest mean probability is selected as the final prediction. The dataset uses Smart Grid Stability Augmented contains 60,000 samples with 14 numerical features. Each represented critical grid parameters that influence system stability, evenly split between stable and unstable states. Features include power, voltage, and other dynamic parameters. These tables compares performance. Bagging and AdaBoost offer solid accuracy with AdaBoost slightly ahead. Stacking achieves high precision and F1 point score. Soft voting excels across all metrics, achieving 97.3% accuracy and an F1 score of 96.2. This figure visually summarizes the comparative performance. Soft voting and stacking dominate across all metrics, affirming their robustness. Bagging and AdaBoost are reliable but not optimal. Here we examine learning curves. All models exhibit good convergence, notably voting and stacking show stable validation accuracy indicating strong generalization. Our framework surpasses many recent methods, including deep learning approaches like GAN-GRID and CNS. While some models achieve similar accuracy, their reproducibility and dataset sizes limit their generalization. The authors 2024 conducted comparative evaluation of single machine learning models like SVM, Canyon, Decision Tree, MLP, and Random Forest using the original Smart Grid Stability dataset, which includes around 10,000 instances with moderate class imbalance. Reported accuracies ranged from 21.0% to 27.4%. In contrast, our proposed ensemble models were trained and evaluated on the Smart Grid Stability Augmented dataset, which consists of 60,000 samples and provides a more balanced distribution of stable and unstable cases. This enhanced dataset offers increased variability and diversity in feature values, contributing to better generalization across models. Our models, particularly soft voting, offer both high performance and particular robustness. In conclusion, our ensemble framework significantly enhances smart grid stability detection. Soft voting and stacking emerged as optimal choices. However, we acknowledge limitations such as static dataset usage, potential generalization constraints, and the lack of dimensionality reduction, which could be explored further. Future enhancements include integration with real-time smart grid data, hybridization with deep learning models, incorporating feature selection or dimensionality reduction to improve scalability and speed. Thank you for your attention. I welcome your questions and feedback on our work.